Now we can talk about the third kind of force in the list. This is called tension. Tension in physics means force. Suppose there's a string attached to a wall and it is in slack position, unstressed, relaxed position. Now when we stretch the string from the other side, the string becomes taut and straight. If we try to pull it more, the string becomes more and more straight and tight. And the tension in the string is set to increase, and it will become more difficult for us to move, to pluck the string in the perpendicular direction, because the tension in the string would be very high. Now what happens is, when we try and pull the string from one end, or when we try and pull the string from both ends, then the material strength of the string that resist the motion of the molecule away from each other, and there is some attractive force at molecular level that tries and brings the molecule of the string closer to each other, back to its initial position. So we want to stretch outward and the string wants to come inward. So there is some inherent force at the molecular level that tries and bring the molecules closer to each other, and it becomes more and more difficult for us to stretch the string more and more. So although the string will be stretched to a very minuscule level, and in that range the force of attraction at the molecules will become so high that it will be very difficult for us to stretch the string any further, and if we keep on increasing the force, at one point the string will break. But the thing is, there will be some inward force acting in the string that will be against our force. So suppose we are applying a force F outside in outward direction by our hand, and let's cut this section of the string and analyze what are the forces acting on that. Suppose this is the portion of the string. A force F is being acted on it by our hand. Now this string is not moving. This string is in static equilibrium condition. From Newton's first law, if it is at rest and it continues to be at rest, that means there is no net external force acting on it. So the net external force should be 0. For this string, this force is external force, and the force from rest of the string, that is also external force for this part of the string. So if it has to be 0, and on the other side, if tension is acting on the string, which we represent by T, then T must be equal to F. Then only this part will stay in equilibrium. And suppose if we cut a larger section from here, then also on this side force F is acting, and on the other side force T should be acting, and T should be equal to F because it is in equilibrium, it is not moving. Similarly, we cut the string from any portion and we take any section and analyze the forces acting on that. One end will be the force, the other end will be the tension. If we cut a section from middle, then on both the side of this string there would be tension. And these two should be equal. That means tension in any part of the string will be the same, because the whole thing is in equilibrium. So this is very important for us to understand that the tension in the string will be uniform and will be the same in every part of the string. It won't go on decreasing as we go away from the source which is applying the force. The tension will be uniform if it is in a static condition, and it will be the same at each and every point, and that tension will be equal to the applied force. If the system is not moving, if it is an equilibrium condition, then these two must be equal. Okay, now that's one. Another important thing here to understand is tension acts away from the body. For example, if we come to this point and think of as to in which direction the tension would be acting away from the wall. Because we're trying to stretch the string, we're trying to bring the molecules away from each other, and the molecules want to come closer to each other, back to its initial position, and they go against the stretch. So actually this wall and this hand is actually stretching the string away, outward. So the molecules want to come inward. So the tension at this point will be away from the wall, and tension at this point will be away from the hand. It will be away from the mass. Tension acts away from the body. For example, this is a block and this is a string, and suppose you are pulling the block via string. So when you are pulling the block via string, then the block will come along with the string, and the direction in which the tension will act on the block will be in the direction you are moving your hand. So if you look at the block, since the block is moving and suppose the surface is frictionless, it's perfectly smooth. There is no drag force, there is no resistance from the surface. The only force which is moving this block is this tension. And since the block is moving in the right hand side, so the tension should be acting in the right hand side. So the tension is acting away from the body, it is not acting towards the body. And that is very easy, very intuitive for us to understand, because the string will be in a stretched condition and the molecule wants to come closer, so they would be coming closer. So this is the direction in which the tension would be acting. For the body, it will be away from the body. For the hand, it will be away from the hand. Tension always acts away from the body. For example, if a mass is hung with a string like this, suppose it's 1 kg of mass, then there is some tension in the string, because this weight will try to pull the string downward due to its weight, due to the force of gravitation, and the string will tend to stretch, and due to that stretch there is some internal force developed that tries to bring the molecules closer. So the tension will try to bring the molecules back to its initial condition. So the tension in this case will be acting upward for the block. Okay, so tension acts away from the body, and tension for a static rope is uniform throughout the rope, and that is equal to the external force which is applied. In this case, the external force, if you look at the forces acting on this block, one is mg and the other one is tension upward. This block is not moving, that means this mg and this tension must be same. Mass I have given as 1 kg, so mg will be 1 into g. The value of g is very close to 9.8, but it will be good enough if you take it as 10. It will be almost good enough, but generally you should take the value 9.8, but for convenience I'm taking here as 10. So the force which is acting downward is 10 Newton. So the tension should be equal to 10 Newton. It should be equal to the applied external force. Okay, so this is one of the forces that very frequently will be dealing with this in this chapter and the chapters which are coming next.